Hey, welcome back to Ye Old Foundry, back in my office. Recently I just put out a video. Recently I put out a video that described tin bronze, also known as gunmetal, leaded tin bronze, known as valve bronze, and high leaded tin bronze, also known as hydraulic bronze. Gave you some ideas on how they were used, why they were developed, and so forth and so on. And I kind of told you about how, because of its alloy, tin bronze in many cases was the go-to bronze when it came to just general purpose castings. That's what we usually used. It was inexpensive, and it had enough strength that if you just used it as it was supposed to be used, for instance, like dogging down the door with just your hand, and maybe help with the use of a wrench instead of hitting it with a hammer, the dog would last considerable amount of time. Okay, maybe decades, but often that didn't happen, and so hence the reason why we usually made dogs for both our ship and any ships that had come alongside and had a maintenance period scheduled with us. Now, let's say you are in your foundry and you will need to make a casting. It's got to be very good on the corrosion side when when it comes to the corrosion of metals that are going to be on a boat, especially on a boat that's going to be on salt water. And it's got to be very, very strong. Okay, we used to use manganese bronze to cover those requirements. Okay, now I have no idea why manganese bronze was called manganese bronze, and I'll show you why. Okay, I hope you don't get too dizzy when I move you around, but if you know anything about the brasses and bronzes, you know that bronze is typically a mixture of copper and tin. Tin, being a lot more than any other alloying additive. Now, brass is supposed to be an alloy of copper and zinc, okay, and is typically stronger than bronze, right? Well, manganese bronze, for the longest time, I didn't realize it wasn't a bronze. Nobody knows where that was named, how it was named, why it was named manganese bronze. Okay, of the books that I've read trying to research it, nobody alluded to the reason why it's called manganese bronze. Okay, I'll show you. I'm hoping, maybe at this angle you'll see it easier. Okay, and I'll put this in the center. You'll see on the top line manganese bronze. Next line is high strength yellow brass. Manganese bronze is not a bronze. Copper for manganese bronze is 60 to 66%. Tin is 0.2%. Okay, so it's not a bronze. Lead 0.2%. Zinc 22 to 28%. That in itself should tell anybody that that's a brass. But I guess in the future, if you hear the word manganese bronze, hear the name manganese bronze, it's not a bronze, it's a brass, and just keep that under your hat and you'll be smarter than other people who've never looked it up. Okay, manganese bronze, when you break it down, 60 to 66% copper. Where's my pointer? Okay, 0.2% of tin, 0.2% of lead, 20 to 28% zinc, iron. Yeah, you can melt iron in copper. 2 to 4%, nickel 1%, aluminum 5 to 7.5%, and here's manganese. You notice that this could have been called aluminum bronze because aluminum's got more in it than manganese, but they did. Anyway, 2.5 to 5% manganese. Its tensile strength is greater than many as a non-ferrous material is greater than some ferrous materials. Okay, these you can get different combinations of alloys and still be under the heading of manganese bronze. But this one I got off of the durabarnes.com website. They've got a whole lot of different other alloying, tables on their site if you're interested to look up a particular alloy. High strength yellow brass, 55 to 60%. Less than 1% of tin. Less than 0.4% of lead. 39% of zinc. Greater than manganese bronze. Iron is between 0.4% and 2%. Nickel, less than 1%. Aluminum, 0.5 to 1.5%. Manganese, 1.5%. And its tensile strength is 71,000 pounds per square inch. Also, being a non-ferrous material, has better tensile strength than some of the ferrous materials. Now, we also know that ferrous materials, I'm not talking stainless steel, which is very expensive if you're a foundry. They'll be stronger, but their corrosion resistance was crap. Okay, as soon as you start putting ferrous materials underwater or even above water, but you're surrounded by salt water, the salt in the air, the splashing of salt water on the ship when you're underway, it all starts corroding it right away. And if you don't want it to corrode away before its life or its projected life, you're going to have to add things nearby, like zinc plates, to which will allow the zinc plates to corrode before the steel will corrode. Okay, now just for curiosity's sake, the military specs for manganese bronze is Mil C 2222-9, grade 9. The old number, I knew it was a Mil B. I didn't remember what the number was. The old military spec number was Mil B 16443. High strength yellow brass, military spec Mil C 15345, grade 3. The old number, Mil B 17511. Okay? Put my little pointer right there, and I'll take you back to the desk. Okay, now put this. When I was on my first ship, the USS Fulton AS-11, AS being a submarine tender, it was a very old ship. Okay, I think it's gone now. It's been broken down and made into what we normally say is just razor blades. But I think its history, in the 80s, it was sold to Turkey, and they didn't keep it very long for some reason. Maybe it just didn't fit their needs, and it was scrapped. Okay, on the Fulton AS-11, typically our customers were submarines. Okay, now because of the Thresher disaster in, I think it was 68 or 69, the late 60s, prior to my coming in, there was a system that was set up called the sub-safe system. Anything and everything that was put on a sub had to pass this sub-safe system, and castings were really looked at hard. because it was determined by the investigation that what happened is when the Thresher was diving, one of the valve bodies like maybe cracked or burst, which caused flooding in the sub, and they just went down so far that they imploded into numerous pieces. And so, having determined that, they decided that there was a certain level of quality that had to be maintained, had to be developed before any castings and other things that had to be strong would ever go on a submarine. Well, in our little old foundry on the Fulton, we not only didn't have all the equipment required to make the castings better than the typical castings we would make, but we also hadn't developed the techniques quite yet. Okay, there were some ships, some subtenders that had developed the techniques and had gotten the equipment that they were able to pass a lot of their castings as sub-safe castings. And typically when the Navy starts off a new program, they really make almost everything impossible to be achieved. And then over time, they finally realized that their quality levels were beyond our abilities, and so they may have brought them down just a smidge, but yet still had to be very strong castings. We couldn't do it in the Fulton. No sub-safe castings jobs were given to us. So what they wound up doing is we wound up doing a whole lot of cable jobs, or rather on the subs. I myself went on the sub, and on the forward and aft portions of the ship above deck, there were emergency buoys. They call them emergency buoys, and when the ship or the boat goes down to a certain level, these emergency buoys pop loose and go straight up to the top of the ocean if the cable is long enough, and they're there to mark where the sub has gone down. And they typically will only pop loose if they hit bottom, and will only be seen if they're where they hit bottom. The cables will allow the bright orange bottom of these buoys to reach the top, and the what is that? International orange. It was international orange color, so that anybody could see it, easily. Now, our job in the Fulton for the submarines, the only one that we really kept, and because we did a good job on that, was to add the the sockets to the wires, which then was connected to the emergency buoys. Okay, so I was able to get on the subs and do that work, but mainly a lot of the stuff we did is we made andirons, and I don't know if you know what an andiron is. If you ever look at a fire place, and you have something in there that allows you to put logs on it that keep it up off the brick underneath it, typically it'll be a steel square stock, I guess. Typically steel square stock. It's got a leg in the back, a leg in the front. It's got a piece of square stock that goes the depth of the fireplace, and then it goes up a 90 degrees, and on this 90-degree portion you would put whatever artistic thing you wanted to put on there. In the case of the Fulton, the ones who what they wanted mostly is our dolphins andirons. Now it's not a caricature of a dolphin. What we're talking about is that on the submarines, it's a requirement for every sailor to learn every system on the submarine so that, you know, if somebody, like, let's say they have battle damage, or they hit bottom for some ungodly reason, and there's damage, and the guy who's in charge of that area of the vessel has been put out of action, anybody else should be able to go in there and repair what was destroyed or what was damaged, and put the ship back into, I mean, the boat back into operation. And if you get qualified on a submarine, on every system on there, you get a pin that you can put on the left side of your, I think it's still the left side of your uniform, and they're called dolphins. Okay, maybe I'm going to try and find a picture of the dolphins so you can see what it looks like. If I can't, then you just realize that there's a submarine in the middle and a dolphin on the right, dolphin on the left, right, left, and you know, it's actually a very highly sought metal, that, or rather a pin that you put on your uniform, and it's a requirement. You know, so you're not going to get away if you're going to stay on that sub at all. You've got to work and pass the requirements of learning all the systems. So we would make andirons. I guess the HT shop would make the steel part, and we in the foundry would make the brass part. And the brass part was about so tall to so tall, depending. You know, and I think most of the officers were getting that, because we didn't make that many to give to ordinary crewmen. Okay, either senior petty officers or the officers requested that. Might have even just been commanding officers. Okay, then beyond the andirons, we made plaques, and these were the plaques that were the command's symbol of that command. Okay, let's see if I've got. Do I have anything here? Yes, I do have. One moment, I'll be right back. I was able to I was able to save the master pattern for the USS Thresher. Now, when the USS Thresher went down, the Navy didn't want any more plaques to be made, okay, which would kind of, you know, have a negative effect on the fact that everybody died on that ship. It would like be disrespectful to those people who gave their lives. You know, you got to show them the honor of their sacrifice, and they thought that if anybody made any more of these brass plaques, you know, that would belittle the sacrifices they had made. And so the order was given and passed down to the foundry, to whomever was in charge at the time, that the master pattern was to be destroyed. Okay, apparently somebody had some sense, and what they did is they went and put it up in a storage area, and if anybody ever really came by and said, was it destroyed, they must have said, yeah, we melted it down. But when I was on there, I was either a third class or I mean, I made second class before I left the ship. So second class to fire MLFA, somewhere in there, they had me cleaning on top where the storage area was, and I found this, and I got permission to take it home. Okay, my biggest regret was the fact that I took it off the molding board. Okay, it was on a nice molding board, to be, you know, the kind that you put in a 12 by 12 flask. And what I did is I went and scraped all the pattern, the wax away that was making the fillet, popped it off, put this in a bag, and then took it home. Okay, the molding board would have been, let's say, oh, that wide. I would say, well, this distance up to here all the way around, and I wouldn't have been able to hide the fact that I was taking it off the ship by any imagination. Okay. Now, example of a ship's symbol. This was the Thresher's design and symbol that was supposed to represent the ship. Okay. Every command has got their own little plaque, their own symbol to for them. We made bunches of plaques. Now, and they were typically being awarded to people that were re-enlisting or retiring, or maybe got some other good thing given to them, and then the command wanted to give them something. And the ship's plaques, not everybody got them. The guys who were in the Navy and were just the ordinary sailor, didn't cause any waves, didn't really bust their butt to do anything special, probably didn't get any. We would make 20 or 30 of them in a pour. It would take a couple of days to take the excess flashing off of it, and on the Fulton, the vast majority of the plaques we made, we buffed. They were beautiful. They were made of manganese bronze. Okay, high strength yellow brass, and when you buffed them good, they were bright golden color. They were beautiful. The problem was, see the detail on this. Now this has never been buffed because it was going to be a master pattern, and we were going to be using this to make brass plaques, and then after that it was going to be buffed. Well, look at all the detail you have in here. Okay, most of that detail has to be, when it's being buffed, is a lot of the surface detail is taken away. Okay, so any of the thin stuff, like for instance the nuclear atom thing right here, that would be almost gone, but they wanted bright shiny brass plaques. All right, so we did that, and it was a dang shame because it takes a lot of effort to try and get that level of detail to come out in a sand mold. Not so hard for it to come out if they make a die mold, a machine out of die to pour molten metal into that die, because that's made out of stainless steel, and it's going to be as smooth as as you can see. The stuff mostly you see now on plaques, they aren't sand molds. They're not being made with sand molds. They're being, somebody's going to make a $10,000 mold out of stainless steel, and you can, where a sand mold, you can make one plaque, break it down, mold the sand, and make a new mold. The stainless steel molds, you can make 50,000 of them before they start losing any of their detail. Okay, so but it takes a lot of time and a lot of money to make that stainless steel mold. So most everybody didn't want to do it that way. They accepted the pebbly surface of a sand mold, because it turns out it would turn out nice and golden looking and really, really sharp looking. After spending a few years on the Fulton and just buffing all my hard-earned detail off the plaque, decided that I'd never buff another plaque. If I was ever in charge, what we were going to be doing is we were going to be antiquing the plaques. And what would be a good... Here, let me go ahead and I've got plaques out on the my wall over here. Had to put them somewhere. Let's see if I can turn on the lights. There we go. Now, here's the plaque that I buffed to a high sheen And you can see how, it's, see the AS11 right there? That's almost gone. A lot of the stuff is almost gone. So I didn't like that at all because of all the work we had to do. This, while this is a plastic plaque, this is the type of effect, or rather what it would look like if you were making out of brass or bronze, making out of bronze. We usually use bronze. And we acid treated it. And then once the acid treating was dark black like this, we would take some light sandpaper and all the highlights, we would just make it to where it would show. I don't have anything good here. Oh, this is better. This is off the Piedmont that I was on. All of this stuff would be highlighted with sandpaper, and then the finish would be a light coat of clear, clear spray. It'd be like varnish or something. It's clear. Here is one that I buffed, and because it's so close to the light, it's a little bit shinier yet. But you can see how, like, look at the AS11 on the bow. Half the stuff is rubbed away by the buffing wheel, which I didn't like because it kind of denigrated the efforts that any molder put out to make the plaque as best he could. Okay? Anyway, now we're back and we're going to be talking about manganese bronze and high strength yellow brass. I have before me Cast Metals Handbook by the American Foundrymen's Society, which was printed in 1957. Okay, that I was 4 years old when this was printed, so that was 61 years ago. But these older books still have are still an excellent source of information. Now, I have an area in here describing manganese bronze, and I'm going to make sure that I have the pages all set up. Okay, and I'm going to read directly from this this book, because I wouldn't be able to give you the same information as smoothly as they've written it here. Okay, takes about 6 minutes thereabouts to read through, and so I'm going to while I'm reading this, I have 3 tables that I've taken pictures of that you might want to copy down. It gives all the information. I took pictures of them, and if they came out good, which I have no doubt that they should have, they give you information that, all the information that they have. Not only do they have the breakdown of the copper alloy like I showed you over there, but they also have mechanical properties such as tensile strength, yield strength, elongation percentage, reduction of area, modulus of elasticity, Brinell hardness, compressive strength, impact strength, physical constants. In table 35.15, high strength yellow brass, manganese bronze. Physical constants they will show you, or is the melting point, pouring temperature, light castings, heavy castings. Well, the pouring temperature for light castings and the pouring temperature for heavy castings, the specific gravity, the weight per cubic inch, pattern maker's shrinkage, electrical conductivity, thermal conductivity, coefficient of thermal expansion, specific heat, solidification range, and they give the sources by which they came from this. Okay, a lot of this information you won't care about. You may care about a lot of this information if, for instance, you were trying to develop a casting that's going to perform a certain function, and you're trying to, and you know how strong it's got to be. You know how, you know what kind of, pardon me, an environment it's going to be in. So scope out these three tables I'm going to show you, and I'm going to have that on the screen rather than you just staring at me reading out of a book. Okay, so at this point I will start reading. Manganese bronzes are essentially copper-zinc alloys with varying amounts of alloying elements such as manganese, iron, and aluminum. They are among the strongest copper-based alloys and have excellent corrosion resistance properties. They are relatively easy to cast but have high shrinkage characteristics, and consequently careful consideration must be given to gating and risering systems. They are not subject to heat treatment, but retain their unusually high as-cast characteristics with little or no difficulty as long as attention is paid to chemical composition. In other words, don't skimp on the copper, zinc, and lead, and so forth. The high-strength yellow brasses, or manganese bronzes, have been defined by the ASTM, the American Societies of Testing Materials, is what that means, as copper-based alloys containing over 17% zinc with less than 6% tin, and over 2% total of aluminum, manganese, tin, nickel. Why did they put in tin again? Somebody screwed up the printing. Let me start that over. And over 2% total of aluminum, manganese, nickel, and iron, with both silicon and lead under 0.5%. The leaded manganese bronzes meet these same requirements, but the lead exceeds 0.5%. Manganese bronze is melted in most any kind of furnace used in common practice in the foundry industry. However, the major part is melted in individually fired crucible furnaces, either stationary or tilting, and utilizing either gas or oil as fuel. Don't forget, this was printed in 1957. I would change that portion to now it's probably all being melted in induction furnaces. But don't forget, if they said that it was typically being melted in the gas or oil fueled furnaces, you with propane gas should be able to do it too. Manganese bronze has also been successfully melted in low frequency induction type furnaces, which is what I was mostly exposed to in my military career, and there is considerable use of open flame and reverberatory type furnaces for the melting of manganese bronze. If you want to know what the reverberatory type furnaces are, I gave a real good video on furnaces, and I suggest you watch that, and if you want to know what a reverberatory type furnace is, it'll tell you. As with the other bronzes, the temperature of pouring is of primary importance. The metal should be poured at the highest possible temperature at which it will not show an excessive flare. Because of the low boiling point of zinc, close control of the melting equipment is necessary to maintain the uniformity of alloys. Now, when they talk about excessive flare, on the Fulton, when we were making, heating down the manganese bronze for the molds that we had on deck, which was making plaques, typically what we would do is we would bring it up to the temperature at which we started having a column of zinc flakes rise from the metal. Okay, as soon as that started happening, it almost looked like volcano, vapors coming off of a volcano. At that time, we would shut down the furnace. We would clean the metal, scrape the inside of the crucible, and then scrape off the stuff that rose to the top, and then pour the castings. And then when the people around us saw how much, zinc was in the air, we at one point they started making us go down and have some, drink some milk and stuff. One time they'd made us do that, and nobody bothered after that. Okay, the alloy should never be superheated as is not necessary, and should be avoided since it is accompanied by a high zinc losses, which would change the composition and materially alter the physical properties. In other words, the strength of the zinc wouldn't be in the alloy anymore, and you wouldn't have that tensile strength that you're aiming for. The use of fluxes is not recommended when melting in crucible or electric furnaces, since the alloy tends to form a protective film from its own dross. However, in open flame melting, a cover of flux is useful in protecting the melt from adverse effects resulting from impingement of open flames. Now, the reason why they're worried about impingement of open flames is because in those open flames, not all of the fuel has been burnt. Some of that fuel, especially if it's oil-fired furnace, some of that oil will not have been totally burnt up, and the material will get into your molten metal. Okay, then you'll have junk that you don't want. It'll mess up your metal. Okay. In casting manganese bronzes, the molding sand has properties in which a considerable latitude is permitted. The film of alumina carried on the surface of manganese bronze gives a fair finish even in rather coarse sand. Generally speaking, sand with permeability of 40 to 100 and a green compression strength of 8 to 12 psi is usually satisfactory for most casting operations. It should be mentioned that the alloy is quite susceptible to damage by excessively wet sand. Consequently, the sand in the foundry should be worked slightly on the dry side. It is not common practice to use a facing sand except in very special cases. If the molding sand falls within the foregoing specifications, it will be fine enough to impart satisfactory smoothness to the casting. Oftentimes, a facing on heavy castings may be necessary to stop scabbing around the area of metal entry, especially when the top side of the casting is flat at the entry point. Because of its high shrink characteristics, unusual attention must be paid to... I thought I put a gosh darn piece of paper in there. To the gating and risering systems for individual castings. Reference should be made to reliable information available on gating and risering systems recommended for this alloy. Chills may often eliminate the need for excessive risering. However, because of the drossing tendency, care must be taken in the proper use of chills. Choke gates, strainer cores, and pouring basins should be arranged to allow the metal to enter the molds without turbulence. Okay, high stress was put on no turbulence for a copper alloy when I was writing, or rather I was making those videos about the gating systems. Hot tops and insulated sleeves are frequently used in casting manganese bronzes for their insulating properties on the riser. Hot tops and insulated sleeves, exothermic material, something that will, flame off and act as an insulator from the sand around it to keep that stuff in the riser sleeve, keep that molten for as long as they can. And the topping, it's an exothermic sleeve you can ram up inside the mold, and it'll be there for when you pour it and the molten metal rises into the riser void. But if you was to go ahead and leave that top exposed to the atmosphere, it would start freezing up there. So what they do, as soon as that gets up there near the top, they'll take a scoop and they'll pour some of the same type of exothermic material that the sleeve is made of, and that'll flame off for a short period of time and then become a insulator against the outside atmosphere, and that riser will stay as hot, it'll stay molten for a considerably greater amount of time, certainly long enough to allow the casting to draw from it and fill in any places that might have been a shrinkage if there wasn't any risers. Okay, hot tops and insulated sleeves are frequently used in casting manganese bronzes for their insulating properties on the riser, which affords better feeding to the casting itself. Manganese bronzes, as a rule, is not difficult to handle in the foundry, and sound, dense castings of unusually high strength and good corrosion resistance can be easily cast if the foundry pays proper attention to chemical control, melting practices, and uses a good gating and risering system. Now, that is one of the best explanations for high-strength yellow brass, also known as manganese bronze. In San Diego, where I was able to be exposed to a great many larger projects, we used to make some of the supports for under the boats. Gee, minis, I wish I could remember that. Studs? No. Anyway, it'll come to me. I'll try and make a, if I can find my drawing stuff. Alright. Anyway, what you have, you're trying to make supports for the shaft that comes out of the boat, and on the end of that shaft has the propeller. Okay, so you've got the ship. You have a pad goes on this side of the ship. You have a pad that goes on that side of the ship. These pads are screwed into the hull, and trying to remember. Anyway, let's see. Let's say that's a little bit bigger. Wait, and then down here you will have a hole that the propeller shaft will come through. Let's say this is the item we're making. And it would be like that. Okay, these pads are attached to the hull. This comes down to receive the shaft, and this acts as a bearing to hold this in place while, to support the shaft. So this shaft, when it comes out of the hull of the ship, won't just bend the first time something hits it, or the first time they have some bad seas. Okay, we made a bunch of those out there, and they were quite large. They were probably 4 foot tall if you stood it up, and might have weighed 250 pounds. Okay, the reason why they used manganese bronze is because of the corrosion resistance and the high strength. Okay, high strength, low speed. Right? If it was they wouldn't make it as part of an electrical motor. They wouldn't make it as part of a tranny, casting, because of it'll be strong, and it can absorb vibration from low speed turning, but it would certainly not handle anything high speed. And when they made those struts, that's the name, I knew it would come to me sooner or later, struts, they would just like the like what I read, you didn't have to hardly do anything to them other than just get rid of the flashing or the excess metal that might be on the outside edges, and it would be pretty. They never bothered to paint them because they had their own. It had its own oxidized surface that wouldn't go any further than that. You know, it would only get just so dark, and then it would stop. Corrosion would stop at that point. I mean, that's not to say it would last 1,000 years, but many of these struts that came on the that supported the shafts, the propeller shafts, they lasted for the life of the boat. Okay, now that's not to say that these struts are made of that same material for larger boats, like rather something that is actually known as a ship, like destroyers and bigger. Maybe even some of the big ocean-going tugs might have stainless steel, but 50-footers, 60-footers, utility boats that are used for running back and forth from the ship to, let's say, the shore and all that, those certainly would have the struts that would hold the propeller shafts. Okay, and this is the end of that. That's all I wanted to. I added a little bit of information from what we used to make when I was in, and so, relatively speaking, this is going to be a shorter video. So I'll try and find something else that you might like to have the information for, that might help you on any projects that you might be working on. If you can make manganese bronze, it's a great, strong material. Negative side, it does have a lot of shrinkage, so you'll have to make a lot more risers. You have to use risers more often. But it'll not only give you, if you're making an ornamental casting, it'll be a beautiful golden casting if you buff it, and it even still looks pretty good if you just antique it and highlight the detail. If you need to make something that's, for instance, there's a fella over in Britain who helps his buddy who has steam. Earthquake. He maintains steam engines, and he's got a big a steam like a big truck. Okay, it looks like a big dump truck almost, but I think it was set up for hauling, supplies and stuff back and forth in the days that they were actually used a lot. Anyway, there's portions on there that go bad because of its age, and this fella uses Petrobond sand to make brass. Uses scrap, but that's a good example of the stuff you can use. It's highly resistant to corrosion. It's very strong, so the steam wouldn't just blow it apart once you got up to steam pressure. The only other thing that would even be better for that application would be for Monel, and Monel just might be a material that I'm going to cover very soon. Okay, so everybody out there that's trying to be a good molder or founderman, do your best. Don't get hurt, don't get burnt. Safety equipment's there to keep you from getting killed and burned up. And if you have any questions, for instance, if you have any of the materials, some, it's nothing super exotic because I don't have that big of a book collection. So ask me about it. I'll try and get you what you need. All right. So to everybody that's in the Navy or was in the Navy, Liberty Call, and the rest of you, thumbs up. Try and keep that energy going and receiving, and always suck in that information. It'll only help you in the long run. I'll see you later. if I can turn this off.